Right now, you exist. Your eyes are moving across this screen, your heart is beating, photons are entering your retinas, neurons are firing in a brain made of atoms that were forged inside dying stars. And none of it had to be here. Not the screen, not the stars that made the atoms, not the space those stars existed in, not the laws of physics that built the stars, not even the capacity for anything to exist at all. There could have been nothing. Absolutely nothing. No space, no time, no quantum fields, no laws, no potential, no possibility. And the question of why there is something instead of that nothing is the question that every physics equation you have ever encountered quietly assumes away. Tonight, we chase it all the way down. Subscribe and get comfortable, because the answer keeps getting stranger the deeper we go. There is a question that has been sitting at the center of human thought for as long as human thought has existed, and yet it is a question that most physicists will tell you is outside the domain of physics, which is itself a strange admission for people whose entire project is the description of everything that is. The question is 4 words: why is there something? And the more carefully you sit with it, the more it refuses to behave like other questions. It refuses to be answered by any equation currently written. It refuses to be answered by pointing to any prior cause, because any prior cause is itself something that requires the same question. It refuses to be dissolved by saying the universe has always existed, because that is just pushing the question backward in time without eliminating it. It is, in the most precise and non-dramatic sense of the phrase, the question that breaks physics. And tonight we are going to find out exactly how and why it breaks physics, what physics has tried to say about it anyway, and what remains genuinely, openly, permanently beyond the reach of every theoretical framework human beings have constructed. Let me start by telling you what makes this question different from other hard questions in physics. And this difference is not subtle, it is categorical. When physicists face a hard question, the standard procedure is to identify what we know, build a model that accounts for it, generate predictions, test them against observation, and refine the model. This process has been spectacularly successful. It has given us quantum mechanics accurate to 11 decimal places. It has given us general relativity that correctly predicts the timing of GPS satellites to the nanosecond. It has given us the standard model of particle physics that describes the behavior of every known fundamental particle with a mathematical structure elegant enough to fit on a coffee mug. The procedure works. It has worked for 350 years with a consistency that makes it the most reliable tool for understanding the physical world ever developed by anything that has ever existed anywhere. But the procedure has a hidden assumption buried inside it. Every single time we apply it, we are assuming that there is a world to build models about. We are assuming that there are things to observe, things to test, things to measure. The procedure for doing physics assumes the existence of a physical reality as its starting point, which means the procedure cannot, by design, ask why the starting point exists. That question is not harder than other questions in physics. It is a different kind of question entirely. It is the question underneath physics, the question that physics stands on without examining, the question that has to be answered before physics begins, and which physics, therefore, cannot answer. And this is not a trivial or temporary limitation. This is a structural feature of what the discipline of physics is. Gottfried Wilhelm Leibniz, the German philosopher and mathematician who in the 17th century co-invented calculus and spent considerable effort thinking about why the universe was the way it was, articulated the question with a precision that has not been improved upon in 350 years. He wrote that nothing happens without a sufficient reason, that there must be a reason why it is so rather than otherwise. And then he looked at the totality of contingent things, all the things that exist in the world, everything we can see and touch and measure, and he asked the obvious follow-up question: What is the sufficient reason for the existence of this totality itself? Why is there a world of contingent things rather than no world at all? This is the question that Leibniz called, in his own terms, the fundamental question of metaphysics. And what he meant by calling it fundamental was not that it was the most difficult. He meant that it was logically prior to everything else. Before you can ask any other question about the world has to exist. And nothing in logic or mathematics or physics tells you that it should. Martin Heidegger, the 20th century German philosopher who made this question the centerpiece of his work, opened one of his most famous lectures with the statement that the question of why there is something rather than nothing is the fundamental question of metaphysics, and added that it is not an arbitrary question. It is the first of all questions in terms of rank. He meant that it precedes every other question, that it has a priority over every other inquiry, that until this question is at least acknowledged, everything else is built on an unexamined assumption. And it is a striking thing about the history of thought that for most of it, this question has sat in a corner being acknowledged and then moved past. Philosophy acknowledges it and then turns to other things. Science acknowledges it and then explicitly sets it aside as outside the domain of science. Theology claims to answer it, but the answer either creates a new version of the same question or dissolves into mystery. And yet the question does not go away. It sits there underneath everything, as patient and persistent as the emptiness it is asking about. The first thing we have to do if we are going to take this question seriously is understand what would actually count as an answer. Because the question has a very specific structure that makes certain kinds of answers immediately fail. The question is not asking why the universe has the particular features it has, why it has this particular amount of matter, this particular set of physical laws, this particular collection of constants. Those are hard questions and we will come to them, but they are downstream of the fundamental question. The fundamental question is asking why there is anything at all, why the total inventory of existence has any entry in it whatsoever, rather than being a completely empty list. And any answer that works by invoking something that exists fails immediately and completely. If you say the universe exists because of the laws of physics, you have just invoked the laws of physics, which are something rather than nothing, and the question becomes why the laws of physics exist. If you say the universe was created by a god, you have just invoked a god, which is something rather than nothing, and the question becomes why the god exists. If you say the universe came from a quantum vacuum, you have invoked a quantum vacuum, which is something rather than nothing, and the question becomes why the quantum vacuum exists with its particular properties and not some other kind of vacuum or no vacuum at all. Every answer that moves the problem back one step rather than eliminating it leaves the question standing. And this is not a minor inconvenience, it is the central structural problem with the question. Any answer to it that points to something existing as the reason generates a new version of the same question about that something. There are really only three categories of position one can take about this question. The first is that the question has a genuine answer, that there is a reason why something exists rather than nothing, and that this reason can in principle be understood. The second is that the question is malformed, that it contains some conceptual confusion that, once identified, makes it dissolve in the way that asking what happened before the Big Bang might dissolve into the observation that time itself began with the Big Bang. The third is that the question is genuine and unanswerable, that existence is simply a brute fact with no reason behind it, that the universe just is, and no further explanation is available or necessary. Each of these positions has serious defenders among the most careful thinkers who have ever addressed the question. And tonight, we're going to follow each one of them into the territory where it leads, because the territory is strange, and the strangeness is instructive. And we're going to follow the physics as far as it goes, and then note precisely where and why it stops, because even the places where the physics stops are telling us something about the structure of the problem. The silence of physics at the edge of this question is data, and it is data of a specific and interesting kind. Let us begin with the position that physics has actually come closest to occupying. The position that the question might be slightly malformed, that what we think we mean by nothing, the absence of everything, the total negation of all existence, might not be a coherent concept, that nothing might be impossible, not impossible in the way that traveling faster than light is impossible, which is a contingent physical impossibility that depends on the specific laws of our universe. Impossible in the deeper way that a square circle is impossible, that the concept contains a contradiction. And the argument for this position comes from an unexpected direction. It comes from inside physics itself. It comes from quantum mechanics. The quantum mechanical vacuum is the state of lowest possible energy. It is the state you get if you take a quantum field, cool it down as much as thermodynamics allows, remove every particle, and look at what remains. What remains is not nothing. What remains is a seething, fluctuating, active medium that produces real, measurable effects on things embedded in it. This is not a speculation or a theoretical artifact that careful analysis might remove. The quantum vacuum is directly observable, and the most direct observation of it is something called the Casimir effect, first predicted by the Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed by Steve Lamoureux at the University of Washington in 1997. Here is the Casimir effect in its simplest form. Take two flat metal plates and place them very close together in a complete vacuum. Not a partial vacuum, not a low-pressure environment, but as close to genuine empty space as you can produce in a laboratory. Remove every particle, cool everything to as close to absolute zero as possible. The plates should feel no force between them. There is nothing between them to push or pull. No air, no gas, no field, no particle. And yet they attract each other. They are pushed toward each other by something that is not there in any ordinary sense. Something in the empty space between the plates and the empty space outside the plates is different, and the difference produces a real, measurable force. The explanation comes from quantum field theory. The electromagnetic field, the field that underlies all of light and all of electromagnetism, cannot be exactly zero anywhere in space. This is a direct consequence of the Heisenberg uncertainty principle. If the field were exactly zero at some point, you would know both its value and its rate of change precisely, which is forbidden. So the field fluctuates. It fluctuates everywhere, even in a region with no particles, even in the emptiest space you can construct. And these fluctuations are what physicists call virtual particles, which is a somewhat misleading name because they are not really particles in the conventional sense, but they are real fluctuations in the quantum fields that permeate space. They are the quantum fuzziness that the Heisenberg uncertainty principle guarantees cannot be removed. Now, between the Casimir plates, only fluctuations whose wavelengths fit in the gap between the plates are allowed. The plates are conductors, and conductors enforce boundary conditions on the electromagnetic field. Outside the plates, all wavelengths of fluctuation are allowed. This means the fluctuation pressure outside the plates exceeds the fluctuation pressure inside, and the result is a net inward force, pushing the plates together. The force is tiny. Measuring it required instruments of extraordinary sensitivity, but it is real, reproducible, consistent with the quantum field theory prediction to a precision of about 1% in early experiments and better in subsequent measurements. The quantum vacuum has a real, non-zero energy, and it pushes things around. What this means for our central question is something quite specific. The quantum vacuum is not nothing. It is a quantum state. It is the ground state of quantum field theory, the lowest energy state of the collection of quantum fields that make up our best description of matter and energy. This ground state has properties. It has energy, it has geometry, it has fluctuations with specific statistical characters governed by specific mathematical laws. The quantum vacuum is something. It is a very particular kind of something, something defined by its relationship to all the quantum fields we know about. But it is not the nothing that the fundamental question is asking about. And here is where an important distinction needs to be made carefully, because it is often blurred in popular discussions of this topic, and the blurring is where a lot of confusion enters. The physicist Lawrence Krauss wrote an influential and genuinely interesting book called A Universe from Nothing, in which he argued that physics has essentially answered the question of why there is something rather than nothing. His argument was that the quantum vacuum can spontaneously produce universes that quantum fluctuations in an empty quantum state can tunnel into an inflationary expansion, that there is a physical mechanism by which a universe like ours can emerge from a quantum ground state. This is a real argument about real physics. The mechanism he is describing is taken seriously by cosmologists. Eternal inflation and the production of bubble universes from a quantum de Sitter background is a genuine theoretical framework that many serious physicists work within. But Krauss was explicitly and directly challenged on the philosophical question by the physicist and philosopher David Albert, who pointed out in a review that a quantum vacuum is not nothing. A quantum vacuum is a physical object with properties. A quantum vacuum is something. The laws of quantum field theory that govern the behavior of the vacuum are something. The distinction between a quantum vacuum fluctuation that produces a universe and one that does not is governed by specific rules that are something. When Krauss says the universe came from nothing, what he means is that the universe came from a quantum vacuum described by quantum field theory, which is a perfectly good cosmological claim but is not an answer to the fundamental question. The fundamental question asks why there is a quantum vacuum governed by quantum field theory rather than nothing at all. And to this question, physics has nothing to say, because physics begins from the quantum vacuum and its laws, and does not explain why those exist. This is not a small point. This is the point, because the question has a very specific target, and that target is not the absence of particles or the absence of matter or energy in some region of space. The target is the absence of everything. The absence of quantum fields, the absence of the laws governing quantum fields, the absence of the geometry within which the fields live, the absence of the logical structure that would allow anything to be the case about anything, the absence of space, time, logic, mathematics, possibility, and the capacity for anything to happen or be described or exist in any way. That nothing is what the question is asking about. And any answer that describes a physical mechanism for producing something from any kind of prior state is not answering the question. It is rerouting around it. This is enormously important to understand and not easy to hold in the mind for long, because the human brain is very good at thinking about things and very poor at thinking about the absolute absence of everything, including the absence of things to be absent from, including the absence of the concept of absence itself. When we try to picture nothing, we tend to picture dark, empty space, a void, a featureless vacuum. But dark, empty space is something, a void is something, a featureless quantum vacuum is something. The nothing that the question is asking about is not a physical vacuum or an empty room or a mathematical zero. It is the total negation of everything that could be described by any word in any language or any symbol in any formal system. And the strange thing is that we cannot coherently picture this, which raises an interesting sub-question. Can we coherently conceive of it? And if we cannot coherently conceive of it, is the question itself coherent? This is the second position we identified, the position that the question might be malformed. And the argument for malformation goes like this. The concept of nothing that the question requires might be self-defeating. Nothing defined as the total absence of everything might be a concept that collapses under analysis, because if there is truly nothing, there are no properties, no laws, no constraints, no possibilities, no impossibilities. But the total absence of constraints is itself a kind of state. A state in which anything is possible is a state. A state is something. And so even the most radical nothing we can try to describe turns out to have some structure, some character, some content, even if that content is negative. The nothing that we imagine is not really nothing. It is a placeholder for something we cannot fully specify, a word pointing at a region of concept space that may not actually be occupied by any coherent idea. The philosopher David Lewis, in his work on modal realism, made an interesting argument that all possible worlds exist, and that what we call our world is simply the one we happen to be in. If Lewis is right, the question of why something exists rather than nothing has a trivial answer. Everything that could exist does exist. Our universe is one of the things that could exist, and so it does. Nothing would be the complete absence of all possible worlds, which on Lewis's view is not actually possible, because the set of all possible worlds includes every consistent description, and the complete absence of all descriptions is not itself a consistent description. This is a genuinely interesting position, and it has been taken seriously by a number of philosophers, but it faces the obvious objection that it simply redefines existence in a way that does not match ordinary usage and does not actually explain why anything exists, only asserting that all possible things exist without explaining why possibility itself should be actualized. The physicist Max Tegmark has taken a related but different position, one that begins from inside mathematics rather than outside it. Tegmark's mathematical universe hypothesis is the claim that our universe is not merely described by mathematics, but is identical to a mathematical structure. If Tegmark is right, the question of why a mathematical universe exists has a different structure than the question of why a physical universe exists, because mathematical structures, unlike physical objects, seem to have a kind of necessary existence. The number 7 is not something that was created by any physical process. The theorem of Pythagoras was not brought into existence by the Big Bang. Mathematical truths seem to be true in a sense that does not depend on anything physical existing to make them true. If our universe is identical to a mathematical structure, then its existence might be as necessary as the existence of the number 7. The universe would not be a contingent thing that might or might not have existed. It would be a necessary thing, a mathematical truth that could not fail to be true. We will come back to Tegmark in detail because his position raises deep and strange questions about the nature of both mathematics and physical existence. But for now, what is important is the general move that Tegmark is making. He is arguing that the question of why something exists rather than nothing might have a different character than it appears to have if we recognize that existence comes in different kinds. Physical existence and mathematical existence might not be the same thing, and if mathematical structures exist necessarily, and if physical reality is identical to a mathematical structure, then physical reality exists necessarily too. The something that exists does not require an external cause. It could not fail to exist. This is an audacious claim, and it faces serious objections. The first and most immediate is the old problem that Leibniz himself identified with necessary existence arguments. Even if we grant that some things exist necessarily, there remains a question about which necessary things exist. Mathematics contains many structures. Most of them are not our universe. Why is our universe the specific mathematical structure that corresponds to physical reality and not some other structure or no structure at all? This is sometimes called the problem of the selection of laws. Even if laws of physics necessarily exist as abstract mathematical objects, there is still the question of why these particular laws are the ones that are physically realized, meaning the ones that have instances, the ones in which things actually happen. And here we begin to connect the fundamental question to one of the most pressing open problems in modern physics. the fine-tuning problem. The observation that the laws of physics, and in particular the constants that appear in those laws, take values that are extraordinarily precisely calibrated for the existence of complex structures and ultimately life. The universe we inhabit is one in which the constants of nature have a very specific set of values. The strength of gravity is what it is. The mass of the electron is what it is. The strength of the electromagnetic force is what it is. The mass of the Higgs boson is what it is. And in every case, these values are very precisely what they need to be for the universe to have any interesting structure at all. The cosmological constant is perhaps the most dramatic example of this kind of fine-tuning, and it is directly relevant to the question of why something exists rather than nothing. The cosmological constant is a term in Einstein's field, equations of general relativity, that describes the energy density of empty space. The measured value of the cosmological constant is very small. It corresponds to an energy density of roughly 7 times 10 to the power of negative 27 kilograms per cubic meter, which is an extraordinarily small but non-zero number. It is small enough that the universe can have the large-scale structure we observe, galaxies and clusters forming over billions of years rather than being torn apart immediately by a rapidly expanding space. Now, quantum field theory also makes a prediction about the energy density of empty space. This prediction comes from the zero-point fluctuations of all the quantum fields that exist. Every quantum field contributes to the vacuum energy. You add up all the contributions from all the known fields, apply the standard procedure of quantum field theory, and you get a number. The number you get is roughly 10 to the power of 120 times larger than the measured value, not 10 times larger, not 1,000,000 times larger, 10 to the power of 120 times larger, which is, to put it bluntly, the largest discrepancy between a theoretical prediction and an experimental measurement in the history of science. It is not close to being a rounding error. It is a mismatch of so many orders of magnitude that physicists call it the worst prediction in the history of physics. And yet, the measured value is what it is. The cosmological constant does not have the value that quantum field theory predicts. It has a value that allows the universe to have its observed structure. If the cosmological constant were as large as quantum field theory naively predicts, the universe would have expanded so violently and so rapidly in its earliest moments that no matter could ever have clumped together. No galaxies, no stars, no planets, no atoms in stable structures. The universe would have been shredded into a thin gas of particles expanding so fast that nothing could ever interact with anything else. There would be something, in the strict sense, that there would be particles of some kind distributed through an expanding space, but there would be nothing interesting, nothing complex, nothing that could observe itself. And the difference between the universe we actually have and this uninhabitable universe is a number, the cosmological constant, that quantum field theory says should be 10 to the power of 120 times larger than it is. Something has to explain why it is not. The 3 mainstream responses to this cosmological constant problem reveal 3 very different approaches to the fundamental question of existence. The first response is that we have made a mistake in the calculation. That quantum field theory, despite its extraordinary empirical success, is getting something wrong about how vacuum energy contributes to the cosmological constant. That some cancellation we do not yet understand, some symmetry we have not yet found, reduces the vacuum energy contribution to approximately 0 and leaves only a tiny residual from some other source. This is the response of most theoretical physicists who work on the problem. It is the response that says the problem is a real one, but has a real solution that will be found by better understanding the physics. The problem with this response is that despite 50 years of effort by the best theoretical physicists in the world, no such cancellation mechanism has been found. Supersymmetry was for a long time thought to be a promising candidate because supersymmetry cancels the contributions of bosons against those of fermions in a way that could reduce the vacuum energy substantially. But supersymmetry, even if it exists, does not reduce the cosmological constant to zero. It reduces it but leaves a residual still many orders of magnitude too large. And moreover, supersymmetry has not been experimentally confirmed at the energies the Large Hadron Collider at CERN has probed. The second response is the anthropic principle. This response says that we should not be surprised that the cosmological constant has the value it does, because if it had any other value, we would not be here to observe it. If the cosmological constant were much larger, the universe would have expanded too fast for structure to form, and there would be no observers. If it were much more negative, the universe would have collapsed before structure could form, and again, there would be no observers. The fact that we observe a cosmological constant in the range compatible with the existence of observers is not a coincidence but a selection effect. We can only observe a universe that allows us to exist. And so, of course, the universe we observe has a cosmological constant in the range that allows us to exist. This argument is formally valid but philosophically unsatisfying to many physicists. And the reason it is unsatisfying is that it does not actually explain the fine-tuning. It explains why we observe fine-tuned values given that we exist. But it does not explain why a universe with fine-tuned values exists for us to be in. For the anthropic argument to do any explanatory work, there must be many universes with many different values of the cosmological constant. If there is only one universe with one value of the cosmological constant, and that value happens to be compatible with observers, then the anthropic argument is useless as an explanation. The coincidence would remain a coincidence. The anthropic argument only removes the coincidence if there is a vast ensemble of universes with different constants, so that any particular value has a natural place in a distribution, and our observation of a life-compatible value is simply a matter of us being in one of the life-compatible ones. This brings us to the third response, which is the multiverse. And the multiverse, in the form it takes in modern theoretical physics, is not a speculation in the casual sense. It is a prediction of the most successful cosmological framework we have, which is inflation. Inflation is the theory that in the very early universe, within the first tiny fraction of the first second after whatever we call the beginning, the universe underwent a period of exponential expansion, driven by the energy of a scalar field called the inflaton. Inflation was proposed by Alan Guth in 1980, extended and refined by André Linde, Paul Steinhardt, and others, and is now supported by observations of the cosmic microwave background with a degree of quantitative agreement that goes beyond mere consistency. The specific predictions of inflation about the spectrum of density fluctuations, their statistical properties, and their scale dependence match what the Planck satellite has measured to a degree that has few parallels in cosmology. In the version of inflation developed primarily by André Linde, known as eternal inflation, the inflationary expansion never globally ends. In any given region, inflation can end when the inflaton field rolls down to the bottom of its potential and the energy is converted into the particles and radiation of the hot Big Bang. But quantum fluctuations continuously kick the inflaton field upward in some regions, restarting the inflationary expansion there. The result is that while individual regions stop inflating and become what we call bubble universes, the space between bubbles continues inflating, exponentially generating new volume faster than any finite rate of bubble nucleation can fill. Inflation, in this picture, is eternal to the future. It never stops. And within this eternally inflating background, bubble universes form continuously and may have different properties. In the context of string theory, which is the leading candidate for a theory that combines quantum mechanics and gravity, the inflationary potential has an enormous number of local minima, each corresponding to a different set of physical laws and constants. Estimates of the number of these minima range from 10 to the power of 500 to much larger numbers. Each bubble universe that nucleates in the eternally inflating background may settle into one of these minima, giving it one of the corresponding sets of laws and constants. The result is an enormous ensemble of bubble universes with every possible combination of constants that the string landscape allows. In this ensemble, the cosmological constant takes every allowed value. Some bubble universes have a cosmological constant large enough to prevent structure formation. Some have a cosmological constant negative enough to cause recollapse before structure forms. Some have a cosmological constant in the narrow range compatible with the existence of complex structure and observers. We find ourselves in one of the last kind, not because this kind was specially arranged, but because only this kind contains observers to find themselves anywhere. The multiverse framework, combined with the anthropic principle, provides a genuine and non-circular explanation for the fine-tuning of the cosmological constant. It does not require fine-tuning to be a brute fact. It explains fine-tuning as a selection effect in a vast ensemble of universes with different constants. And this is arguably the best explanation for the cosmological constant currently available. It is not universally accepted, and it faces serious objections that we will examine. But it is a serious scientific framework with real mathematical content, not a vague gesture at possibility. However, and this is a large and important however, the multiverse does not answer the fundamental question. The multiverse does not explain why there is something rather than nothing. The multiverse replaces one something, our universe, with a larger something, an eternally inflating background with many bubble universes. This larger something is even more something than the original something. It is an enormous collection of physical realities governed by the laws of quantum field theory and general relativity, and it requires all the same explanatory infrastructure that our original universe required, plus more. The multiverse moves the cosmological constant problem and the fine-tuning problem from the realm of coincidences to the realm of selection effects, which is a genuine improvement in our understanding. But it moves these problems within the realm of something. It does not address why there is any realm at all. Here is the structure of the explanatory problem in its sharpest form. To explain the cosmological constant, we invoke the multiverse. To explain the multiverse, we invoke eternal inflation. To explain eternal inflation, we invoke the laws of quantum field theory and general relativity and the specific potential energy landscape of the inflating field. To explain these laws, we might invoke some deeper theory, perhaps string theory, which has its own axioms and mathematical structure. To explain why string theory describes physical reality rather than being merely a mathematical structure, we are back to the fundamental question. At every level of the explanation, we invoke something. And the question of why there is that something rather than nothing is never closed. It is simply moved to a higher level, where it sits, waiting, unchanged. This is the sense in which the question breaks physics. It does not break physics by producing a contradiction within physics. It breaks physics by being prior to physics. It is the question that physics cannot ask, because asking it requires stepping outside the framework that physics operates within. Physics describes the behavior of the physical world, but the question of why there is a physical world is not a question that the physical world or the laws governing it can answer. Because any answer that appeals to physical laws is already inside the thing that needs to be explained. Let us now look at what Stephen Hawking attempted to say about this question. Because Hawking was one of the most creative theoretical physicists of the 20th century, and his attempt to address the fundamental question is instructive, both for what it accomplishes and for what it leaves open. Hawking's most direct engagement with the question came through the no-boundary proposal, which he developed with James Hartle beginning in the early 1980s and described at length in his popular book, A Brief History of Time. The no-boundary proposal is a framework for quantum cosmology, a way of applying the methods of quantum mechanics to the universe as a whole, rather than to individual systems within the universe. In ordinary quantum mechanics, you describe the state of a system by its wave function, and the wave function evolves according to the Schrödinger equation in time. But if you want to describe the universe as a whole, there is a problem. What is the time with respect to which the wave function of the universe evolves? Time is part of the universe. You cannot have the wave function evolving in time if time is one of the things the wave function describes. This leads to what physicists call the problem of time in quantum gravity, and it is one of the deepest unresolved conceptual problems at the intersection of quantum mechanics and general relativity. Different approaches to quantum gravity handle this problem differently, but all of them have to confront it. The Wheeler-DeWitt equation, which is the quantum gravity analog of the Schrödinger equation for the universe as a whole, has no explicit time dependence. The universe, described by the Wheeler-DeWitt equation, does not evolve in time. It simply exists as a wave function on the space of all possible three-dimensional geometries, called superspace, without any preferred time axis. We discussed this in a previous video, and it is relevant here because the no-boundary proposal is a specific attempt to choose the wave function of the universe by specifying its boundary conditions. Hartley and Hawking proposed that the wave function of the universe should be computed by summing over all compact, Euclidean, four-dimensional geometries with a given three-dimensional boundary. The key word here is compact, meaning closed and without boundary. In Euclidean quantum gravity, which is the formalism Hartley and Hawking used, time is rotated into an imaginary direction, making it geometrically similar to a spatial direction. The result is that the beginning of time is treated not as an edge or a boundary of space-time, but as a smooth interior point. The universe, in the no-boundary proposal, has no temporal beginning in the sense of a hard edge where the geometry stops and nothing begins. It has an interior point where the time direction smoothly emerges from a spatial configuration, the way the south pole of a sphere is a smooth point with no edge, even though it is the point from which every direction is north. Hawking used this analogy explicitly, asking what happened before the Big Bang in the no-boundary framework is like asking what is south of the South Pole. The question is not wrong because the answer is mysterious. The question is wrong because the geometry does not have a south of the South Pole. There is no boundary at the South Pole beyond which nothing exists. The south direction simply runs out at the pole. Similarly, the time direction in the no-boundary geometry simply emerges smoothly from a spatial direction at the initial point, without there being a boundary beyond which nothing exists. The universe in this picture has no external cause and requires no creator, because it has no beginning in the sense of an edge that needed to come from somewhere. This is a genuinely interesting and creative proposal. It is mathematically well-defined, at least approximately, and it makes specific predictions about the quantum state of the universe that in principle can be compared to observations. The amplitude for various initial conditions is computed by the no-boundary wave function, and those amplitudes can be used to predict probabilities for the large-scale properties of the universe. Inflation, in some versions of the calculation, is a preferred outcome of the no-boundary initial conditions. The universe we observe might be a natural prediction of a universe described by the no-boundary wave function. But the no-boundary proposal has faced serious criticism, both technical and conceptual. On the technical side, a series of papers by Neil Turok and collaborators in the late 2010s argued that the no-boundary wave function, when computed with the methods of Lorentzian rather than Euclidean quantum gravity, does not produce the well-behaved inflationary initial conditions that Hawking claimed. The calculation appears to give the opposite sign for the exponent, predicting that the most probable initial conditions are the least homogeneous rather than the most homogeneous, in contradiction with what we observe. Hartley, Hawking, and others contested these criticisms and proposed modifications to the calculation But the status of the no-boundary proposal remains genuinely uncertain within the technical community. It is not the established, widely accepted framework that Hawking's popular presentation sometimes implied. On the conceptual side, there is a question about what the no-boundary proposal actually says about the fundamental question. Hawking sometimes presented it as an answer to why the universe exists, but the no-boundary proposal is a description of the boundary conditions of the universe's wave function. It is a choice about how to compute the wave function of the universe. It does not explain why there is a universe described by any wave function. It does not explain why there are laws of quantum gravity that determine how the wave function evolves. It does not explain why mathematics of the kind that quantum mechanics and general relativity use describes physical reality. The no-boundary proposal pushes the question back one step by replacing the question of why the universe has a specific initial state with a particular rule for computing the initial wave function. But the rule itself is something, and the question of why that rule exists rather than nothing is the same old fundamental question again. Hawking himself in his final years seems to have recognized this and adopted a position that sounds almost like the third position we identified, the position that existence is a brute fact. In his final book, Brief Answers to the Big Questions, published posthumously in 2018, Hawking wrote that the question of why there is something rather than nothing arises from a confusion. He argued that because there is a law like gravity, the universe can and will create itself from nothing. But this answer contains exactly the problematic move we have been tracking. Because there is a law like gravity, why is there a law like gravity? What is the sufficient reason for the existence of the laws of physics? Hawking's answer does not eliminate the regress. It just names the level at which he is willing to stop. And stopping at the laws of physics is a choice, not an explanation. The laws of physics are not self-explanatory. They are not logically necessary. They could have been different or they could not exist. This brings us to what Sean Carroll, the Caltech theoretical physicist, has argued is the most honest position about the fundamental question. Carroll's position, which he has articulated in papers, books, and lectures with characteristic clarity, is that existence is a brute fact, and that this is not a failure of explanation, but simply the correct description of how explanation works. Carroll argues that any complete explanation of reality must bottom out somewhere. It must reach some level of description that simply is, that has no further explanation behind it, that is not caused by anything else. The question is not whether such a bottom exists, because for any finite chain of explanations, there is always a bottom. The question is where the bottom is. And Carroll's position is that we have no reason to believe the bottom of the explanatory hierarchy is at any level above the laws of physics themselves, or above the quantum state of the universe, or above the particular structure that happens to exist. This position is philosophically defensible and scientifically honest. It says that we should not expect the universe to explain itself any more than we should expect a mathematical proof to prove its own axioms. Every system needs axioms that are taken as given. Physics is a system. Its axioms are the laws of physics and the initial state of the universe. Asking why those axioms hold is asking the system to prove its own foundations, which is something Gödel's incompleteness theorems tell us cannot be done from inside the system for sufficiently powerful formal systems, and which seems similarly impossible for physical systems. But this position, honest as it is, also feels unsatisfying to many people, including many physicists. And the reason it feels unsatisfying is not merely emotional or theological. There is a genuine conceptual problem with accepting existence as a brute fact. The problem is that a brute fact is arbitrary. If we say the universe just exists without explanation, we are saying it could have been different or could have not existed, and there is no reason why it is the way it is, rather than some other way. But if the universe could have been different, then there is a genuine question about what determines which way it actually is. And if there is no answer to that question, we have accepted a kind of radical arbitrariness at the foundation of everything, a cosmic lottery that has been run once and for reasons we cannot access, produced the universe we inhabit. The physicist David Deutsch, in his book The Beginning of Infinity and in his theory of constructor theory, has argued that good explanations are ones that could not easily have been otherwise, that the best scientific theories are ones where the details fit together in a way that makes changing any part of them destroy the whole. This is an interesting criterion, and it suggests that the fundamental question might be pointing at something real about the kind of explanation we are looking for. We are not just looking for any description of why the universe exists. We are looking for an explanation under which the universe could not have not existed, an explanation under which the existence of something, rather than nothing, is necessary rather than contingent. And this is where we come back to the question of necessity, because the fundamental question has a very specific structure. It is not asking for the cause of the universe in the ordinary sense. It is asking for the reason why contingency itself exists. It is asking why there is a reality that could have been different. And the only kind of answer that would fully satisfy the question is one that shows existence is not contingent at all, that something had to exist, that nothing was never an option. Can physics get there? Can any description of the physical world show that the existence of a physical world is necessary? This is where we have to confront a deep problem about the nature of physical laws. Physical laws describe patterns in the behavior of physical things, but physical laws are not self-enforcing. The laws of physics do not compel physical things to exist the way mathematical theorems compel their conclusions to be true given their premises. The laws of physics say how things behave if they exist, but they do not say that anything must exist to behave that way. This is fundamentally different from mathematical necessity. The theorem of Pythagoras is true of every right triangle, and this truth does not depend on any particular right triangle existing. It is a truth about all possible right triangles in Euclidean geometry, including ones that have never been drawn and never will be. Mathematical truths seem to have a kind of modal force that physical truths do not. They are true not just of the actual world, but of all possible worlds in which their premises hold. This difference between mathematical necessity and physical contingency is the source of Tegmark's motivation for the mathematical universe hypothesis. If we want to understand why physical reality exists necessarily, perhaps we should understand physical reality as fundamentally mathematical, because mathematics exists necessarily. Mathematical structures are not contingent. They could not fail to be the way they are. 2 + 2 could not equal 5 in any consistent mathematical system. The Pythagorean theorem could not be false in Euclidean geometry. Mathematical truths have the kind of necessity that physical existence seems to lack. Tegmark's argument goes like this. Consider any mathematical structure. Does it exist? In mathematics, we would say yes, in the sense that it is well defined and its properties can be deduced, but does it have physical existence? Tegmark argues that all mathematical structures with sufficient complexity have physical existence, in the sense that they have instances, they are physically realized. They have inhabitants who experience them from the inside. Our universe is one such mathematical structure. It is the one we happen to be in. All others are equally real, equally physically existent, just not accessible from here. If Tegmark is right, the question of why something exists rather than nothing dissolves in a very specific way. Nothing in Tegmark's framework would be the absence of all mathematical structure. But the absence of all mathematical structure is itself a mathematical concept, and moreover, it is a kind of impossibility. You cannot have a world that is not described by any mathematics, because a world with no mathematical structure has no definite properties, no regularities, no behavior that could be described. Even chaos in the mathematical sense is structured. Even randomness in the mathematical sense is governed by probability distributions and statistical laws. There is no coherent mathematical concept of a world with no mathematical structure at all. The nothing that the question requires is not a mathematical object. It does not live in the space of mathematical structures. This means that if all mathematical structures exist, nothing in the relevant sense is impossible. Something must exist because every consistent mathematical description has an instance. And the question of why something exists rather than nothing would be answered by pointing out that the alternative, nothing with no mathematical structure, is not a genuine possibility. It is not a member of the set of coherent descriptions of reality because it cannot be consistently described. This is a fascinating argument and it has influenced serious philosophers and physicists, but it faces deep objections. The first and most serious is the objection about which mathematical structures are physically realized. Tegmark needs all mathematical structures to be physically realized, not just some. But we have no evidence that every mathematical structure is physically realized. We have evidence only that this particular mathematical structure, our universe, is physically realized. To get from here to the conclusion that all are requires a leap that seems motivated by the desire to answer the fundamental question rather than by any independent evidence. The second objection is the problem of observer moments. In a framework where all mathematical structures are physically realized, observers in different structures who count themselves as the most likely kind of observer face strange conclusions. A brain floating in an otherwise empty mathematical structure, experiencing a single moment of consciousness, might be simpler and hence more abundant than a brain embedded in an entire complex universe. If all mathematical structures are realized, we should expect to be in the simplest one that contains observers like us, not in an elaborate universe with a 13.8 billion year history. This is the Boltzmann brain problem in a new guise, and it is a genuine threat to frameworks that posit a very large or infinite ensemble of realized structures. The third objection is the problem of mathematical existence itself. Tegmark claims that mathematical structures exist necessarily, but mathematical structures are abstract objects. They do not exist in space or time. They have no causal powers. Nothing in our physical world is caused by the number 7 or by the Pythagorean theorem. Mathematical structures, in the standard Platonist view, exist in some abstract realm that is completely separate from the physical world. But then what does it mean to say they are physically realized? And what is the mechanism by which an abstract mathematical structure becomes physically instantiated as a concrete universe with concrete inhabitants? Tegmark does not have a satisfying answer to this question. He asserts the identification of mathematical and physical existence, but does not explain the mechanism of that identification. These objections do not refute the mathematical universe hypothesis. They show that it is a serious philosophical position with serious difficulties that have not been resolved. Like every other attempt to answer the fundamental question, it has made a genuine contribution to our understanding by sharpening the problem and pointing to deep connections between physics and mathematics. But it has not closed the question. It has revealed new dimensions of the question that were not visible before. Let us now turn to something different. Let us look at what happens when physicists and cosmologists try to describe the actual mechanism by which a universe might come into existence. Not the philosophical question of why something exists, but the more tractable question of how a universe could originate from a state that has fewer properties than the universe itself. This is the question that cosmologists are more comfortable with, and it has produced some genuinely interesting physics, even if it does not ultimately answer the fundamental question. The framework that has gotten the most serious attention in recent decades is quantum tunneling from nothing. The physicist Alexander Vilenkin proposed in the early 1980s that the universe might have originated by a process analogous to quantum tunneling. in which a particle passes through a barrier that it classically should not be able to cross. In quantum mechanics, particles have a finite probability of tunneling through potential energy barriers because the uncertainty principle allows them to borrow energy for a short time. Vilenkin proposed that the universe itself might have tunneled into existence from a state of literally nothing, a state with no space, no time, no matter, no fields. The mathematical description of this tunneling uses the same formalism that Hartley and Hawking used for the no-boundary proposal. You compute a path integral over all compact four-dimensional geometries, and the result is a wave function for the universe that gives a probability amplitude for different possible universes to exist. Vilenkin's approach differs from Hartley and Hawking's in the specific boundary conditions chosen, but the general framework is similar. The universe tunnels from a state of nothing, described by a wave function with zero radius, to a state with a small but non-zero radius, corresponding to a tiny de Sitter space that then inflates into something like our universe. What does the tunneling from nothing actually look like mathematically? In Euclidean quantum gravity, you represent the tunneling trajectory as a compact four-dimensional manifold called an instanton. The instanton connects the nothing state, a single point with zero three-dimensional volume, to the something state, a small sphere with a positive three-dimensional volume. The probability of the tunneling is exponentially suppressed, like all quantum tunneling processes, but it is not zero. Given infinite time, or given a framework in which time itself does not apply to the nothing state, the tunneling will eventually occur. In this sense, something comes from nothing through a quantum process. But again, and we keep returning to this point because it keeps being relevant, the nothing in this calculation is not genuinely nothing. It is a mathematical boundary condition. It is a specific constraint on the wave function of the universe. The wave function itself is calculated using the rules of Euclidean quantum gravity, which is a mathematical framework with specific properties. The framework includes a specific kind of path integral, specific rules for how the integral is computed, specific physical content in the form of the gravitational constant and the cosmological constant. None of these are nothing. They are all something very specifically defined things that the calculation depends on, essentially. Remove them and there is no calculation, there is no tunneling, there is no wave function, there is no nothing from which a something could tunnel. Vilenkin himself has been admirably honest about this limitation. He acknowledges that the nothing from which the universe tunnels is not the nothing of pure negation. It is a particular quantum state. He has argued that this quantum state is as close to nothing as we can coherently describe while still being able to say meaningful things about it. But this is precisely the difficulty. The fundamental question asks about an absolute nothing that is prior to any coherent description, and the tunneling calculation requires a framework within which the calculation can be done. The framework is prior to the tunneling, and the framework is something. There is another version of the question that is equally fundamental and that physics is somewhat better equipped to address, even though it does not ultimately close the original question. This version asks not why there is something rather than nothing, but why the something that exists has the particular structure it has. Why do the laws of physics take the form they take? Why are there 4 fundamental forces rather than 3 or 5? Why is the electron the mass it is? Why is the speed of light the specific value it is? Why does the universe have 3 large spatial dimensions rather than 2 or 7? These questions are downstream of the original fundamental question, but they are more tractable because they are questions about the structure of a something that we can take as given. And here the physics is genuinely interesting. The structure of physical law has been a subject of theoretical investigation for as long as physics has existed, and the 20th century made enormous progress on understanding why the laws take the form they do. One of the deepest insights of modern physics is that the laws of nature are intimately connected to symmetries. and symmetries, in the mathematical sense, are a much smaller and more constrained set of objects than arbitrary laws could be. The electromagnetic force has its specific form because it is required to be invariant under a specific symmetry transformation called gauge symmetry related to the group U1. The weak force is similarly associated with the group SU2, the strong force with SU3. General relativity is associated with the symmetry of general covariance, the requirement that the laws of physics take the same form in all reference frames. The entire standard model of particle physics, which describes all known matter and 3 of the 4 forces, is determined by the choice of a specific gauge group, SU3 times SU2 times U1, and the matter content of the theory. This is remarkable. The detailed structure of all known particle physics is determined by a choice of mathematical symmetry group and a list of fields. Once you choose the group and the fields, the theory is largely fixed. You cannot arbitrarily change the coupling between the electron and the photon without violating the gauge symmetry of the theory. You cannot change the way the gluon mediates the strong force without violating the SU3 symmetry. The laws, once the symmetry is chosen, are not arbitrary, they are constrained. This might seem to offer hope for a naturalistic explanation of the laws. If we understood why the specific symmetry group SU3 times SU2 times U1 was chosen rather than some other group, we might understand why the physical laws are the way they are. But here we immediately hit a wall because we have no explanation for the choice of symmetry group. The standard model is extraordinarily successful empirically, but it is not derived from any deeper principle. The symmetry group is not chosen by any theoretical necessity. It is simply the group that appears to describe the particles and interactions we observe. We do not know why this group and not some other. String theory has been the leading candidate for a deeper framework that might explain the choice of symmetry group and the number of dimensions. In string theory, the standard model gauge group and the matter content emerge from the compactification of extra spatial dimensions and the specific topology of the compact space. Different compact topologies give different gauge groups and different matter content. This is why string theory produces the landscape of solutions we discussed earlier. Different compactifications give different effective physical theories in 4 dimensions, and the observed particle physics is one of many possible effective theories that can emerge from string theory. String theory has produced beautiful mathematics and important insights, particularly the development of the ADS-CFT correspondence, which is one of the most profound results in theoretical physics of the last 30 years. But it has not delivered a unique prediction of the standard model from first principles. The landscape of solutions is not a prediction that all physical theories are equally realized. It is an observation that string theory has many consistent solutions, and we do not yet know which one corresponds to our universe. The dream of a theory of everything that derives the specific laws of our universe from a single elegant principle has not been realized. There is a deep conceptual reason why this dream may be unattainable, and it connects directly to the fundamental question. The dream assumes that the laws of physics are necessary, that they could not have been otherwise, that if you understood physics deeply enough, you would see that SU3 times SU2 times U1 was the only possible gauge group, that 3 large spatial dimensions was the only possible number of large dimensions, that the electron mass was the only possible mass. But there is no evidence that the laws are necessary in this sense. There is every reason to think they are contingent. They could have been different. Our universe is not the only logically consistent universe. Many other consistent mathematical structures with different laws exist as mathematical objects, and whether they are physically realized or not, they exist as genuine logical possibilities. If the laws are contingent, then explaining them means explaining why these contingent laws rather than others. and that explanation must either invoke some higher-level law from which these laws are derived, in which case the higher-level law needs to be explained, or it must invoke a selection mechanism like the anthropic principle operating within a multiverse, in which case the multiverse and its laws need to be explained, or it must bottom out at a brute fact. The regress of explanation always terminates somewhere, and the terminus is always a something that is accepted without further justification. Now let us look at this from a completely different angle. Let us approach the fundamental question from the perspective of logic itself. Because there is an argument that the question of why there is something rather than nothing is not just unanswerable, but is actually incoherent. And the argument comes from thinking carefully about what nothing would need to be. In classical logic, nothing is the empty set, the collection with no members, and the empty set has properties. It is a subset of every set. It has a specific cardinality, 0. It is uniquely defined. The empty set is a well-defined mathematical object. It is not the absence of all mathematical objects. It is itself a mathematical object, one with no members, but still an object. So, in the mathematical sense, even nothing is something. But perhaps the nothing we want is more radical than the empty set. Perhaps we want the negation of all existence, including the existence of logical and mathematical structures. But here we run into a problem. If we try to describe what this radical nothing is, we are already using concepts, language, and logic to describe it. The description itself presupposes the existence of concepts and logic. We cannot coherently describe a state in which concepts and logic do not exist because the description uses concepts and logic. The attempt to think about radical nothing is self-defeating. Every thought about nothing is a thought, which is something. The philosopher Parmenides made this point over 2,000 years ago. He argued that non-existence cannot be thought or spoken, because to think about something is to be thinking about something that exists, at least as a thought. To say that nothing exists is to say something, which means something exists. Therefore, being is and non-being is not. This argument has been criticized for conflating different senses of existence and being, and the criticisms are valid, but the core insight survives the criticism. There is something deeply self-contradictory about the concept of radical nothing. Every attempt to get clear on it seems to generate something. This self-contradictory character of radical nothing has been taken by some philosophers to imply that nothing is impossible, that something must exist, that existence is necessary. The argument is sometimes called the argument from necessary existence of something, as opposed to arguments for the necessary existence of a specific something like God or the universe. It says that the alternative to something, namely nothing, cannot be coherently described or even coherently conceived and therefore cannot obtain. Something must exist because nothing cannot exist. This argument has a certain elegance, but it is not universally compelling. The response is that the incoherence of describing nothing from within a framework of thought does not mean nothing is impossible. It might mean only that we are incapable of thinking about what nothing would be because we are something, and thinking uses something. Our inability to coherently conceive of radical nothing might be a limitation of our thinking rather than a feature of reality. The fact that every description of nothing is itself a description, hence something, shows only that our language and thought are constrained to deal with things that exist. It does not show that nothing is impossible. But here is what is genuinely strange about this position. It says that we are incapable in principle of thinking about the alternative to existence. We are incapable of thinking about what it would be for there to be nothing, which means the question, why is there something rather than nothing, is a question to which we cannot even clearly conceive the alternative. We are asking why the world is one way rather than another way that we cannot think about. This is genuinely strange. It is different from other hard questions in physics, where we at least understand what both alternatives would look like. We understand what a universe with a smaller cosmological constant would be like. We understand what a universe with more dimensions would be like. We do not understand, and perhaps cannot understand, what absolutely nothing would be like. This connects to a point that comes up in the philosophy of mathematics and in the foundations of logic. Certain questions in formal systems cannot be asked from within those systems. Gödel's incompleteness theorems show that sufficiently powerful formal systems contain statements that cannot be proven or disproven within the system, but which are nonetheless true or false. The question of whether those statements are true has to be asked from outside the system, from a meta-level. And the meta-level itself is a system that has its own undecidable statements which require a meta-meta level. The hierarchy never terminates. There is no view from nowhere, no position outside all formal systems from which all questions can be answered. The fundamental question might have a similar structure. It is a question that cannot be asked from within any physical or mathematical system, because every system starts with assumptions that are already something. The question has to be asked from outside every system, from a position that has no assumptions, no axioms, no starting points. But such a position does not exist, or if it does, it is not accessible to any thinking being, because thinking requires a framework. We are trapped inside existence. We can ask the question of why existence exists, but we cannot step outside existence to look for the answer. And this might not be a temporary limitation that better physics or philosophy will eventually overcome. It might be a permanent feature of our situation. There is something almost vertiginous about this conclusion. We are beings made of matter, assembled by the same laws that assembled the rest of the universe. Asking why those laws exist, asking why anything exists, and finding that the very act of asking the question uses resources, frameworks, and capabilities that are themselves part of the thing being questioned. We are the universe asking about itself, and the universe cannot step outside itself to answer. This is not merely poetic, it is structurally the case. Any answer to the fundamental question that a physical being in a physical universe can construct will necessarily be constructed using the physical universe's resources, and any such answer is already inside the thing that needs to be explained. Leibniz recognized this and argued that the answer to the fundamental question had to come from outside the universe. Something that exists necessarily, not contingently. Something that contains the reason for its existence within itself rather than deriving it from something else. Leibniz called this something God. The Leibnizian argument for the existence of God from the principle of sufficient reason is one of the most formally precise arguments in the history of natural theology. It says that the total collection of contingent things, the universe and everything in it, cannot explain its own existence, because explanation moves from effect to cause, and no finite chain of causes within the collection of contingent things will ever terminate the regress. The chain must be terminated by something that is not itself a contingent thing, something that exists necessarily, something that has no cause outside itself because its essence involves existence. This argument is taken seriously by philosophers of religion and by some philosophers of physics. It is not obviously wrong, its premises are defensible, its logic is valid, and its conclusion follows from its premises. The question is whether its premises are true. The key premise is the principle of sufficient reason, the claim that everything that exists has a reason for its existence. If the principle of sufficient reason is true, then the argument goes through and something like the Leibnizian God follows. If the principle of sufficient reason is false or only selectively true, then the argument fails and brute facts are permitted. Physics itself provides reasons for thinking the principle of sufficient reason might not be universally true. Quantum mechanics appears to permit genuinely random events. When a radioactive atom decays, when an electron hits a detector screen, when a photon passes through a polarizer, the outcome is not determined by any prior state of affairs. It is, as far as we can tell, genuinely random in a way that has no hidden cause. The decay happens not for any reason, but simply because quantum mechanics assigns a probability to it, and the probability is actualized without any determining factor. If this is right, if quantum events are genuinely uncaused, then the principle of sufficient reason fails even within the physical world, and if some events within the world have no reason, perhaps the world as a whole has no reason. But this argument is more fragile than it appears, because the randomness of individual quantum events is compatible with the deterministic evolution of the wave function of the universe. In the many worlds interpretation of quantum mechanics, the wave function always evolves deterministically by the Schrödinger equation, and what appears to be random from the perspective of an observer within the wave function is a result of the observer's branch splitting, which is itself deterministic. In the many worlds interpretation, thing is truly random. Everything is determined by the wave function, and the question of why the wave function has the initial conditions it has, and why the Schrödinger equation governs its evolution, is the same kind of question as why the universe exists at all. The Copenhagen interpretation, in which quantum events are genuinely random, does seem to permit events without reasons, but the Copenhagen interpretation has always been philosophically unsatisfying because it requires an unexplained split between the quantum world and the classical measuring apparatus, a split that has never been cleanly defined. The interpretation works as a practical tool for making predictions, but is widely regarded as conceptually incomplete. The search for a more complete interpretation of quantum mechanics, one that does not have the measurement problem as an unsolved central puzzle, has produced many proposals, including many worlds, pilot wave theory, relational quantum mechanics, and others. None of them has achieved consensus. What is clear from all of this is that quantum mechanics, the most fundamental physical theory we have for the behavior of matter and energy, is itself understood only in an approximate and interpretation-dependent way at the level of foundations. We know how to use it. We do not know what it is telling us about the fundamental nature of reality. And this interpretational uncertainty is directly relevant to the fundamental question because different interpretations give different answers to whether the world is deterministic or random, whether the wave function is the complete description of reality or a tool for calculating probabilities, and whether there is anything more to the world than the wave function describes. Let us now go deeper into one of the most interesting and least discussed aspects of the fundamental question, the question of why anything is computable or describable by mathematics at all. Because even if we accept that the universe exists as a brute fact, there is an additional brute fact that seems to cry out for explanation. The universe appears to be mathematical. The laws of physics are written in the language of mathematics with a precision and elegance that has surprised every physicist who has worked with them. Eugene Wigner, one of the founders of quantum mechanics, wrote a famous essay in 1960 called The Unreasonable Effectiveness of Mathematics in the Natural Sciences, in which he noted that mathematics developed for purely abstract reasons with no physical application in mind turns out to describe physical reality with astonishing precision. Riemannian geometry was developed by mathematicians in the 19th century as an abstract generalization of Euclidean geometry, and it turned out to be exactly the right language for Einstein's general relativity. Complex numbers were developed by mathematicians as an algebraic convenience with no physical reality attached to them, and they turned out to be essential to quantum mechanics. Why should this be? Why should abstract mathematics, developed by human minds playing formal games with symbols, turn out to describe the deep structure of physical reality? There are several possible answers. The first is that the universe is mathematical, that mathematics is not a tool for describing reality, but is reality, which is Tegmark's position. The second is that mathematics is a very flexible language, and any structured reality will be describable by some mathematics, so the appearance of mathematical structure in physics is not surprising, but is a consequence of the fact that we call organized things mathematical. The third is that this is a selection effect. Humans evolved to recognize patterns, and the mathematics we have developed reflects the patterns our brains can detect. The parts of reality that are not mathematical simply go unnoticed or are not studied. Each of these answers has something to recommend it, and each has problems. Tegmark's position faces the problems we already discussed. The flexibility of language answer understates how specific and elegant the mathematics of physics actually is. It is not that any mathematics will do for describing reality. The mathematics of quantum field theory and general relativity is very specific, very constrained, and would not have been developed without the physical motivation of trying to describe specific observations. And the selection effect answer, while partly true, does not explain why the most abstract corners of mathematics, developed with no physical motivation, turn out to describe the most fundamental physics. There is something even more specific here that deserves attention. The mathematics of physics has a character that pure mathematics does not always have. Physical mathematics tends to be associated with specific numerical constants, like the fine structure constant, the gravitational constant, the speed of light, and the Planck constant. These constants are pure numbers or combinations of units that take specific numerical values. The fine structure constant, which determines the strength of the electromagnetic interaction, is approximately 1137. Why 1137 and not some other number? There is no mathematical reason. It is just what we measure. And yet if it were slightly different, atoms would not be stable, chemistry would not work, and life would not be possible. The fine structure constant is one of the dimensionless numbers in physics whose value is not explained by any theory. It is measured but not derived. And the question of why it has the specific value it has, like the question of why the cosmological constant has the value it has, is a question that none of our current theories can answer. String theory might, in principle, produce values for the dimensionless constants if we could solve the string theory landscape problem and identify the right compactification. But this has not been done. The numbers that characterize our physical universe at the most fundamental level are unexplained by theory. They are simply the numbers we observe. This is a strange situation. We have a theory of everything, or at least an aspiration to one, that produces a landscape of possible physical theories with different constants. And we live in one of those theories with specific constants whose values we do not understand. The constants are not determined by the theory. They are free parameters that have to be measured. And the question of why those parameters have the values they have is currently unanswered. Now, here is an aspect of the fundamental question that is rarely discussed but is genuinely important. The question of why there is something rather than nothing can be asked at many different levels, and the answers at different levels might be different. There is the question of why any physical matter exists. There is the question of why any physical laws exist. There is the question of why any mathematical structures exist. There is the question of why anything can be the case at all, why there is the capacity for truth or possibility. These are nested questions, each deeper than the last, and the fundamental question in its most radical form is the deepest one. But it is worth noting that even partial answers to the shallower versions of the question would be significant. For example, if we could show that given the existence of mathematical structures, some physical reality must be actualized, we would have reduced the fundamental question to the question of why mathematical structures exist. And the question of why mathematical structures exist might be easier to answer because mathematical structures seem to have a kind of necessary existence that physical things do not. The number 7 could not fail to exist. The theorem of Pythagoras could not fail to be true in Euclidean geometry. Mathematical structures exist in virtue of being consistent, not in virtue of being caused by anything. If we could show that mathematical existence necessarily converts into physical existence for some class of structures, we would have made significant progress on the fundamental question. This is essentially Tegmark's program, and we have already seen its difficulties. But it is worth noting that even without solving all the difficulties, the program has achieved something. It has identified a deep connection between physical and mathematical existence, shown that this connection is not trivial, and raised the question of mathematical existence as a genuine, scientific, and philosophical problem in its own right. Where did the mathematical structures themselves come from? Are they created by something? Do they depend on anything? Or do they simply exist in a way that requires no cause? The standard view in the philosophy of mathematics, called Platonism, holds that mathematical objects exist independently of any mind, any physical reality, any human construction. They exist in an abstract realm that is outside space and time. The number 7 existed before there was anyone to count. The Pythagorean theorem was true before there were triangles, before there was a Pythagoras, before there was a human race to develop geometry. Mathematical truth is discovered, not invented, and this abstract realm of mathematical objects is self-subsistent. Nothing caused it to exist, it just is. If Platonism is right, mathematical existence is indeed necessary. Mathematical structures do not come into existence and cannot go out of existence. They simply are, permanently, timelessly, necessarily. And if physical reality is identical to some mathematical structure, then physical reality shares this necessary existence. The universe could not fail to exist because it is a mathematical structure, and mathematical structures exist necessarily. But Platonism raises its own profound questions. What is the relationship between the abstract realm of mathematical objects and the physical world? If mathematical objects are outside space and time, how do they interact with physical things? How do we come to know about them? How does our physical brain, made of atoms obeying physical laws, access truths about abstract mathematical objects that exist outside the physical world? These are the deep problems of mathematical ontology and epistemology that philosophers have grappled with for centuries without resolving them. And there is a more fundamental problem. If mathematical objects exist necessarily, their existence is still something rather than nothing. The Platonic realm of mathematical truth is a rich, infinite, complex something. It is not nothing. The question of why there is something rather than nothing applied to the Platonic realm is the question of why there are mathematical truths at all. Why is it true that 2 + 2 = 4? Why does the Pythagorean theorem hold? Why is there a mathematical structure at all, rather than the complete absence of any logical or mathematical possibility? This question pushes even beyond mathematics. It asks about the existence of logic itself, the existence of the very capacity for anything to be the case. And here we really have reached the limit of what any formal thinking can address. Logic is the framework within which any thought proceeds. To ask why logic exists is to use logic to examine logic itself. And this is the deepest form of the self-referential problem that the fundamental question embodies. Every tool we have for asking about existence is itself a kind of existence. Every framework we use for investigating the question is itself part of the thing being investigated. Let us now take a step back and look at the full landscape of what we have found. We started with a question that appeared to be a question about physics, but turned out to be a question that physics cannot ask from within its own framework. We found that every physical mechanism proposed to explain existence from nothing actually proposes existence from a more minimal something, which still requires explanation. We found that the mathematical universe hypothesis, while suggestive and creative, does not fully resolve the question because mathematical existence itself is something. We found that the anthropic principle and the multiverse, while providing genuine explanatory purchase on the fine-tuning problem, do not address the fundamental question of why there is any universe at all. We found that the no-boundary proposal is a genuinely interesting framework for quantum cosmology, but does not eliminate the need for laws of physics to govern the quantum cosmological calculation. And we found that the principle of sufficient reason, if applied universally, leads either to a necessary being or to an infinite regress, and if not applied universally, leaves existence as an unexplained brute fact. None of these is a comfortable resting place, and this is perhaps the most honest and important thing we can say about the fundamental question. It does not have a comfortable resting place. Every attempt to answer it either generates a new version of itself at a deeper level or accepts a brute fact that seems arbitrary. The question is designed in a way that prevents any answer from being fully satisfying. It is not that we have not been clever enough or that future physics will fill the gap. The gap has a structural character that is not a function of our current ignorance. And yet, sitting with the question rather than running from it has value. It has revealed things about the structure of physics and philosophy that are important and that shed light on questions that are more tractable. The fine-tuning problem is a genuine problem. The cosmological constant problem is a genuine problem. The interpretation of quantum mechanics is a genuine problem. The relationship between mathematical and physical existence is a genuine problem. The status of the principle of sufficient reason is a genuine problem. None of these are the fundamental question, but they are connected to it, and the effort to think clearly about the fundamental question has sharpened our understanding of all of them. There is also a kind of philosophical value in confronting the fundamental question honestly. We are beings who have evolved in a specific physical environment with cognitive faculties shaped by the demands of survival in that environment. Our intuitions about causation, about time, about explanation, about why things are the way they are, were calibrated by a world in which causes precede effects and explanations appeal to prior states. When we apply these intuitions to the question of why anything exists at all, we are applying them to a domain for which they were not calibrated. The result is a kind of systematic confusion, a feeling that there must be an answer of a familiar kind, that if we just look hard enough we will find the cause that explains existence. But existence might not have a cause in the ordinary sense. It might have a kind of necessity that is different from causal necessity, or it might be a brute fact with no explanation of any kind, or it might be part of a picture that human minds are not constructed to grasp. Each of these possibilities is humbling in a different way. The first humbles us by pointing to a kind of necessity we have never experienced. The second humbles us by suggesting that the deepest feature of reality has no reason. The third humbles us by pointing to the limits of our cognitive faculties in a domain that matters more than any other. There is a fourth possibility that deserves mention because it is taken seriously by some philosophers and has a strange kind of beauty. This is the idea that the fundamental question answers itself, that existence is self-explanatory, that the reason something exists is that the existence of something explains why something exists in the way that the statement, "this sentence is true," is self-referentially true. This is sometimes called the bootstrap view of existence, and it has been defended in various forms by philosophers who argue that a self-referential explanation, while circular in a certain sense, is not viciously circular. It is the kind of circularity that a self-consistent structure can have, where the whole is constituted by its parts and the parts are constituted by the whole. Roger Penrose has explored ideas in this direction in his work on the relationship between mathematics, physics, and consciousness, though his framework is more about the structure of reality than about why reality exists. Penrose distinguishes three worlds, the mathematical world, the physical world, and the mental world, and argues that each world seems to be contained within or emergent from the next in a cyclic way. Mathematics underlies physics, physics underlies mind, and mind accesses mathematics. This is a profound observation about the structure of our situation, but it is not quite an answer to why anything exists. It describes the relationships between three kinds of existence without explaining why any of them exists. The bootstrap view in its strongest form says that the universe is the kind of structure that necessarily exists once it exists, that its existence is self-sustaining, that there is no state in which it would fail to exist once it begins. This sounds like it might be getting somewhere, but it immediately faces the temporal problem. Once it begins, but if the universe exists necessarily, it cannot have begun. A necessary existent does not begin. It simply is. And if the universe simply is without beginning, then the question of why it exists rather than nothing is still open, because the universe could have simply not been timelessly. Unless, of course, timelessly not being is itself impossible. Unless the universe, or something, exists necessarily in the way that mathematical truths exist necessarily, not because of any prior cause, but because the alternative is logically impossible. This is the Leibnizian move applied to the universe rather than to God. Leibniz argued that God exists necessarily because God's essence involves existence, because God is the being whose non-existence is impossible. Can the same be said of the universe? Can we show that the non-existence of everything is logically impossible? This is the argument from the incoherence of nothing. If we can show that the concept of nothing, the complete absence of all existence, is self-contradictory or incoherent, then nothing is impossible and hence something must exist. But this argument moves too fast. Even if the concept of nothing is incoherent to us, this might reflect our own cognitive limitations rather than a feature of reality. The fact that we cannot coherently think about nothing does not mean nothing is impossible. It might mean only that nothing is inconceivable to us. And here we arrive at what might be the deepest insight that the fundamental question generates. The question forces us to confront the limits of what we can coherently think. It forces us to confront the limits of what physics and mathematics and logic can describe. It forces us to acknowledge that our best tools for understanding reality are themselves part of reality, and cannot therefore examine reality from a position outside it. The question is not just hard, it is hard in a specific way that reveals something about the structure of our cognitive situation. We are inside existence, trying to understand why there is an inside, and the inside does not contain the outside. The outside, if there is an outside, is precisely what the question is asking about, and we have no access to it. This is not a counsel of despair. It is an invitation to a kind of intellectual humility that is compatible with continued inquiry, because even without a final answer, the inquiry has value. The inquiry has produced quantum mechanics, general relativity, thermodynamics, the Standard Model, eternal inflation, the ADS-CFT correspondence, and the mathematical universe hypothesis. None of these answer the fundamental question, but all of them have deepened our understanding of the structure of reality in ways that have genuine implications for the question. We know more precisely what kind of something exists. We know more precisely what the laws governing it are. We know more precisely what the connections between physical and mathematical existence look like. We know more precisely what the alternative to existence would need to be and why it is so hard to describe. The question is the oldest question. It preceded physics and will outlast every theory physics has produced, but sitting with it carefully, following it to the places it goes, refusing to accept easy answers that merely relocate the mystery rather than addressing it, is one of the most important things a thinking being can do, because the question is about the fact that we are here at all, the fact that there is a universe, the fact that the universe has the character it has, the fact that in a corner of it, on a small planet orbiting an ordinary star, matter assembled itself into structures capable of asking why any of it is here. That there should be anything at all rather than nothing is the precondition of every other fact. Every discovery, every measurement, every theorem, every experience, every love and every loss and every ordinary Tuesday morning begins from this precondition. And the precondition is unexplained. It is the unlit room at the bottom of the building that everything else is built on. Physics knows how the building works. It does not know why there is a building. It does not know why there is a here for the building to be in. And that silence, that specific and permanent silence at the deepest level of our best understanding, is perhaps the most instructive thing physics has ever produced. Let us now examine this from the other direction. Let us look at what nothing would actually have to be if nothing were possible. And let us see whether examining the concept of nothing more carefully gives us any traction on the question of why there is something. Because one thing we have been somewhat loose about is treating nothing as if it is a single unified concept. In fact, nothing comes in degrees and kinds, and the degree of nothing that the fundamental question requires is much more radical than any nothing that ordinarily appears in physics. In everyday language, nothing means the absence of specific things. The room has nothing in it means the room has no furniture, no people, no objects, but the room still exists. The air in the room still exists. The laws of physics governing the room still exist. This is nothing in the weakest sense. A room with no furniture is something. It is a room. In physics, nothing usually means the vacuum, the state of lowest possible energy, the ground state of the quantum fields. We have already seen that this is not nothing in the fundamental sense. The quantum vacuum has energy, has geometry, has fluctuations, is governed by specific laws. The vacuum is something. It is the most minimal physical state, but it is still a physical state. In mathematics, nothing might mean the empty set, the collection with no members. But the empty set is a mathematical object with properties. It has a specific cardinality. It is a subset of every other set. It is nothing in the set theoretic sense, but it is something in the mathematical sense. The empty set exists as a mathematical object even if it has no members. To get to the nothing that the fundamental question requires, we need to go further. We need the absence not just of matter and energy, but of space, time, quantum fields, and the laws governing them. We need the absence of mathematical structures, including the empty set. We need the absence of logical truths, including the law of non-contradiction. We need the absence of the capacity for anything to be true or false. We need the absence of possibility itself, the absence of any modal framework, the absence of essence, of structure, of property, of relation, the total, complete, radical negation of everything that can be described or even gestured at. This is the nothing that the question is asking about. And the moment we try to describe it, we have failed. We have already used concepts, language, and logic in the description. The nothing we are pointing at is prior to all concepts, language, and logic. It is not a state of affairs. It is not a possible world. It is not even an impossibility in the technical sense, because impossibility requires a framework within which the concept applies. This radical nothing is outside every framework. And here is the genuinely strange insight. If radical nothing is outside every framework, then it cannot be evaluated. It cannot be true or false that it is possible. It cannot be true or false that it ever obtains. It cannot be true or false that something exists rather than it. The question why is there something rather than nothing might be unanswerable, not because the answer is hidden, but because the concept of nothing required by the question is one that cannot be coherently invoked in any proposition. The question might be not just hard, but impossible. Not impossible in the way that solving the halting problem is impossible by a specific theorem, but impossible in the vaguer sense that the question contains a conceptual element that resists all attempts to incorporate it into a meaningful statement. This is different from saying the question is meaningless. The question clearly means something. It points at a genuine gap in our understanding, but it might be the kind of question that points at something real without being answerable by any description, like trying to describe the experience of absolute silence using sounds. The description always fails because using sounds is incompatible with the thing being described. Describing radical nothing is incompatible with the concept being described because description requires something And yet the question persists. It persists because we know we are here, and we know we might not have been. We know that the universe exists, and we cannot see why it could not have failed to exist. The contingency of existence is felt even if it cannot be demonstrated formally. Every person who has ever stared at the night sky and felt the vertiginous sense that all of this might not have been is responding to something real. The somethingness of the world is not felt as a necessity. It is felt as a gift, or a surprise, or a mystery. And that feeling, while not a proof of anything, is a reliable guide that the question is pointing at something genuine. The physicist Richard Feynman once said that the great challenge of physics is to figure out what the laws of physics are, and he noted that if we knew the laws completely, we might not be much closer to understanding why there are any laws at all. This was not a dismissal of the question. It was an acknowledgement that the question has a different character from questions within physics. Understanding the laws perfectly would still leave open the question of why those laws and not others, and why any laws rather than none. Feynman was one of the most practically oriented and anti-philosophical of physicists, and even he recognized this gap. Let us now look at a few of the most radical recent proposals for addressing the fundamental question. Proposals that come from physicists and mathematicians who have been unwilling to accept either the brute fact answer or the God answer and have tried to find a third path. These proposals are speculative, and some of them are barely more than sketches, but they represent the frontier of current thinking, and they reveal what kind of structures people believe might be capable of addressing the question. One of the most striking recent proposals comes from the physicist Julian Barber, whose work on the nature of time we have discussed in previous videos. Barber has argued in a series of papers and in his book, The Janus Point, that the universe might be understood as the expression of a mathematical structure he calls shapespace, the space of all possible shapes of the universe defined purely by the relative positions of particles. Barber's claim is that shapespace is a mathematical object that exists necessarily, in the way that geometrical spaces exist necessarily, and that the history of the universe is a path through shapespace. In this framework, the question of why the universe exists reduces to the question of why shapespace is explored. And Barber's answer is that shapespace as a whole is the structure, and the universe is the exploration of that structure. This is elegant, but faces the standard problem that shapespace itself is a something whose existence needs explaining. Another proposal comes from the philosopher and physicist David Deutsch, whose constructor theory is an attempt to reformulate the laws of physics in terms of what transformations are physically possible. Deutsch argues that the most fundamental facts about physics are not equations governing the time evolution of systems, but constraints on what is and is not possible. The laws of physics in Deutsch's framework are statements about possibility and impossibility. This reformulation might, Deutsch suggests, make it clearer why certain physical laws hold, because the laws express the structure of possibility itself. But even in this framework, the structure of possibility exists, and the question of why there is a structure of possibility rather than no structure at all is still the fundamental question. Perhaps the most philosophically radical recent proposal is the one associated with the philosopher and cosmologist Jim Holt, who in his book, Why Does the World Exist?, engaged directly with the question and interviewed some of the leading thinkers in physics and philosophy about it. Holt's own tentative conclusion after years of investigation is that the question might be approached through the concept of nothingness itself being unstable. The idea is that pure nothingness is not a stable state, that nothingness has a kind of internal instability that causes it to break down into something. This idea has similarities to the quantum vacuum instability that produces virtual particles extended to a more fundamental level. If nothing is inherently unstable, then something is the natural consequence of nothing, and the question of why something exists is answered by the instability of nothing itself. This is an intriguing idea but faces serious objections. The concept of instability requires a framework. Instability is the tendency of a state to evolve toward a different state. But if nothing is truly nothing, there is no framework in which instability can be defined, no time in which the evolution can occur, no different state for nothing to evolve toward. The concept of instability applied to radical nothing imports a framework that radical nothing, by definition, does not have. So the nothingness instability proposal, interesting as it is, does not quite reach the radical nothing the question requires. It addresses a structured nothing that already has the capacity for instability, which is a kind of something. What all of these proposals have in common, and what every serious engagement with the fundamental question has in common, is the recognition that the question is genuine, that it points at a real gap in our understanding, and that it resists every attempt to fill the gap from within the resources of physics, mathematics, or logic. The gap is real. It is not going to be filled by better experiments, or more powerful computers, or more elegant theories. It is a gap that reflects the limits of what any description from inside existence can say about the existence it is inside of. This is not the same as saying the question has no answer. It might have an answer that we cannot construct from inside existence. It might have an answer that only beings outside existence, if such beings are conceivable, could access. Or it might have an answer that is not the kind of answer we expect. Not a causal explanation, but a demonstration of necessity, not an account of how something came from nothing, but a proof that nothing could never have obtained. We do not know which of these is the case. We cannot know from here. What we do know is that we are here. That matter, organized by the laws of physics over billions of years, has produced beings capable of asking this question, that the universe has generated within itself the capacity to be puzzled by its own existence. And this fact, the fact that a physical system has produced consciousness capable of philosophical inquiry, is itself one of the most remarkable features of the something that exists. It is not just that something exists. It is that the something that exists includes minds that can wonder why. The philosopher Thomas Nagel, in his book Mind and Cosmos, has argued that the emergence of consciousness from matter is itself a problem of the same kind as the problem of existence. Why should there be subjective experience at all? Why should matter organized in certain ways produce an inner life, what it is like to be something? This is the hard problem of consciousness, and it is deeply connected to the fundamental question. If we cannot explain why there is something rather than nothing, we also cannot explain why that something should be experienced. Why the universe, in addition to existing, should have an inside view. Why physics, in addition to describing the behavior of systems, should sometimes describe systems that have a perspective on themselves. Nagel's suggestion is that we are missing something fundamental about the nature of reality, something that would explain both why consciousness exists and why the universe exists, something that integrates the objective description of the physical world with the subjective character of experience. He is not proposing a specific theory, he is diagnosing a gap, and the gap he diagnoses is similar in character to the gap the fundamental question identifies. Both gaps reflect the same underlying problem, which is that our best descriptions of reality are descriptions of things from a third-person perspective, a view from nowhere, and the universe might not be reducible to this perspective. The universe includes first-person perspectives. It includes you sitting wherever you are sitting, reading these words, experiencing the strangeness of the question. The universe includes the fact that there is something it is like to exist within it. And no description of the universe written in third-person terms, no equation, no physical law, no mathematical structure fully captures this. The first-person perspective is somehow inside the third-person description, but not reducible to it. And the question of why something exists rather than nothing is partly the question of why there should be anything to be inside of, anything to be experienced from a first-person perspective at all. This is not a new observation. The connection between consciousness and cosmology has been made by many thinkers, and it is sometimes expressed in the form of the anthropic principle, the observation that the universe must be compatible with the existence of observers because observers are what makes the universe observable. But the anthropic principle is a methodological principle, not an explanation. It does not explain why the universe is compatible with observers. It only explains why, given that we are observers, we observe a universe compatible with observers. The question of why a universe compatible with observers exists is not answered by the anthropic principle. It is presupposed by it. We have been following the question of why there is something rather than nothing through physics and cosmology and philosophy for a long time now, and we have found that it leads everywhere and resolves nowhere. Every path we follow turns back and points to the same gap, the gap between any description of existence and the existence itself, the gap between why things are as they are and why there is a why to be answered. And this gap we have been building towards saying might not be fillable from within existence, might be the gap between physics and metaphysics, between science and what underlies science, between understanding and the condition for understanding. But there is one more thing to say, and it is perhaps the most important thing. The question has a transformative effect on the person who asks it seriously. Not because it provides answers, but because it changes what questions feel important. When you sit with the fact that the universe might have not existed at all, that there is no logical or physical necessity for any of it, that every morning of your life has occurred within something that might have been nothing, you start to feel the weight of existence differently. Not in a depressing way, but in the way that paying attention changes what you pay attention to. The ordinary becomes extraordinary, not because it has changed, but because you have changed how you are looking at it. The tree outside the window, the coffee cup, the sound of traffic, the weight of your own body in the chair, all of it is something rather than nothing. All of it is part of the something that exists, and none of it is required to exist by any principle we can identify. The contingency of existence, the fact that all of this might not have been, is not a melancholy observation. It is a radical redirection of attention toward the sheer fact of existence. And the sheer fact of existence, stripped of everything we take for granted about it, is genuinely astonishing. The astronomer Carl Sagan, writing about the pale blue dot photograph taken by Voyager 1 from beyond Neptune, noted that the Earth is a very small stage in a vast cosmic arena. He was pointing to the smallness of our situation in spatial terms. But there is another smallness, or perhaps another vastness, that Sagan's observation gestures toward. The Earth and everything on it, and the universe that contains it, exists within a possibility space that includes the complete absence of everything. In that possibility space, existence is the small thing. Non-existence is everything else. And we are in the small part. We are the something in the infinite field of nothing. Or rather, we are the something in the potential field of nothing, the nothing that might have been but is not. That there should be us here asking this is the question that breaks physics, and physics breaks on it gracefully, honestly, revealingly. It breaks in a way that tells us where its boundaries are, and the boundaries of physics are not the boundaries of everything. They are the boundaries of what can be described by the kind of formal systems that take their starting point from within existence. On the other side of those boundaries is not nothing, not for us. On the other side of those boundaries is a question that we carry with us, that will not be answered in any physics journal or any philosophy text, and that continues to shine precisely because it is not answered. The oldest light in philosophy is still traveling. It has not yet reached its destination, and the fact that it is still traveling, that the question is still alive, is itself a strange and remarkable feature of the something that exists, Now let us return from the philosophical heights and look at some of the most concrete and recent attempts within physics to address questions that are adjacent to the fundamental question, even if they cannot answer it directly. Because even if physics cannot answer why there is something, it might be able to sharpen the question considerably, and sharpening the question has its own value. One of the most interesting recent developments is the study of the fine-tuning problem through a specific technical apparatus called the swampland conjectures. The swampland program in string theory, developed primarily by Kumran-Vafa and collaborators since around 2005 and significantly expanded since, attempts to identify which effective quantum field theories can be consistently embedded in a theory of quantum gravity, specifically in string theory, and which cannot. The landscape of effective theories that can be embedded is called the landscape. The much larger set of theories that look consistent on their own but cannot be embedded in quantum gravity is called the swampland. The swampland conjectures, if correct, significantly constrain the space of possible physical laws. They say that many theories that look perfectly consistent from the perspective of low-energy particle physics are actually inconsistent when you try to incorporate gravity. This reduces the size of the landscape potentially dramatically. Some versions of the swampland conjectures, if true, would rule out de Sitter space, which is the kind of space characterized by a positive cosmological constant as a stable vacuum of any consistent theory of quantum gravity. But we appear to live in a de Sitter space. The cosmological constant we observe is positive. If the swampland conjectures are correct and de Sitter space is not a stable vacuum, then our observed universe is either not a stable vacuum, which would have significant implications, or the swampland conjectures are wrong. This is genuinely controversial within the string theory community. Some string theorists believe de Sitter space is realizable in string theory, just difficult to construct explicitly. Others believe the swampland conjectures are pointing to a fundamental incompatibility between de Sitter space and quantum gravity. The controversy is ongoing, and the resolution will have significant implications for the landscape picture and for our understanding of which physical theories are genuinely possible. But notice how the swampland program relates to the fundamental question. The swampland program is trying to determine which physical theories are consistent in the presence of quantum gravity. It is asking, given that a quantum theory of gravity exists, what can the laws of physics look like? This is a constraint on the laws of physics derived from the requirement of internal consistency of quantum gravity. If the swampland program succeeds, it would reduce the question of why the laws of physics are the way they are, partly answering it by showing that many alternatives are inconsistent, but it would still not answer why there are laws at all, why quantum gravity exists, why any of the required frameworks exist. Similarly, the amplitude-hedron program, developed by Nima Arkani-Hamed, Jaroslav Trnka, and collaborators, has rewritten scattering amplitudes in particle physics in terms of a new geometric object that does not make reference to space-time locality and unitarity as fundamental principles. Instead, locality and unitarity emerge from the geometric properties of the amplitude-hedron. This is a profound reformulation that suggests space-time and its fundamental symmetries might not be the most basic level of description. They might emerge from something more fundamental, something geometric but not spatial. If the amplitude-hedron program and related work on positive geometry and combinatorial geometry succeed in providing a description of physics that is more fundamental than space-time quantum field theory, this would be a significant step toward understanding the structure of physical law from a deeper perspective. It might reveal why the laws of physics take the form they take, in the sense of showing that they follow from a more primitive geometric principle. But it would still be a description of physical law, not an explanation of why any law exists. The pattern we keep encountering is that every advance in theoretical physics deepens our understanding of the structure of physical law without addressing the prior question of why there is any physical law. This is not a criticism of physics. It is a description of what physics does. Physics describes the structure of reality. It does not explain why reality has any structure at all. The question of why there is a structure rather than no structure, why there is something describable rather than nothing at all, is not a question that structural description can answer. Any description, however fundamental, however elegant, however unified, is still a description of something. And the question is why there is a something to describe. We have now been tracing the fundamental question through its many dimensions for a long time. And I want to end by saying something about what all of this means for how we understand the relationship between science and the deepest questions about existence. Science is sometimes described as the most successful method for understanding reality that human beings have developed, and it is. The track record of science in making testable predictions, in building technology, in expanding the scope of what we know, is unmatched by any other human activity. But science, precisely because it is a method, has a domain of application. The method works by making predictions and testing them against observations of the physical world. This requires that there is a physical world, that it is regular enough to be described by laws, that those laws are stable enough to allow predictions, and that observations are possible. These requirements are all assumptions that science makes but does not test. They are the background conditions for science to work. The fundamental question asks about those background conditions. Why should there be a physical world? Why should it be regular and lawful? Why should it be observable by beings within it? These questions are not scientific questions in the sense that they can be answered by the scientific method. They are questions about the conditions that make science possible. And the person who tries to answer them using only the tools of science is in the position of trying to test the assumptions of science using the assumptions of science, which is a circular enterprise. This does not mean the questions are unanswerable by any means whatsoever. It means they require different kinds of thinking, different kinds of tools, different criteria for what counts as a good answer. Philosophy, mathematics, logic, and a kind of disciplined reflection on what it means to exist at all. These are the tools appropriate to the questions at this level. They may not produce the kind of precise quantitative answers that physics produces, but they can sharpen the questions, eliminate false starts, reveal hidden assumptions, and trace the connections between different aspects of the problem. And there is one more thing they can do. They can sit with the mystery honestly, without pretending it is solved, without filing it away as unanswerable and therefore unimportant, without reducing it to something smaller that can be managed. The fundamental question is genuinely hard and genuinely open and genuinely important. It is the question underneath all other questions. It is the question that the universe, through us, is asking about itself. And the most intellectually honest response to it is not an answer but a posture of sustained, careful, serious attention. We are beings made of matter, assembled by physical processes in a universe that might not have existed, asking why anything exists. This is not a tragedy or a failure of science. It is the universe becoming aware of its own improbability. It is matter generating the capacity to wonder about the fact that it exists. And that fact, the fact that there is something capable of being surprised by the something, is perhaps the strangest and most beautiful aspect of the something that exists. The question will not go away. It will be asked by everyone who ever stares at the night sky long enough, by every physicist who traces an explanation back far enough to hit the ground floor, by every philosopher who follows a chain of reasoning until it runs out of footing. And it will keep breaking physics in the same place, at the same depth, not because physics is insufficient, but because the question is prior to physics. It breaks physics at the exact point where physics meets its own foundation and cannot look beneath it. The question is 4 words. Why is there something? And the universe, which is the something in question, has spent at least 13.5 billion years assembling the equipment necessary to ask it. You are part of that equipment, and the fact that you are asking, the fact that the question is alive in a mind built from hydrogen and carbon and the laws of physics in a universe that did not have to exist, is perhaps the closest thing to an answer that the something has been able to offer about itself so far. Not a logical proof, not a physical derivation, but an existence asking about its own existence. The question folded back on itself. The something that is here wondering why. That wondering is not nothing. That wondering is the universe at its most self-aware. And until we find something better, it might be the closest we can get to the answer. Sleep with that thought tonight. You exist. You did not have to, and you know it.